Okay. Actually, I prepared 46 page.
Okay.
Yeah, I minimized the page,
Okay.
but I think everyone will slay.
Okay.
I'm a little worried about that, actually.
Don't worry.
Okay.
Later, just send the PowerPoint to us via email. Yeah.
Okay. Is it okay to send the PDF?
It's fine. It's fine.
Okay.
It is just for the reporting purposes only.
Sorry?
It is just for the report to the agency.
Okay, okay. So just you need some verification documents.
Yeah, we need some kind of proof. One of them is the slide.
Okay. So 47 people entered the entered the room.
We haven't allowed to enter the room for the participant at this time.
Okay.
Just wait for 5 minutes before.
All right. So this is first time to see this kind of scheme. There is some waiting room, and then there is some delegates for presentation. So the audiences will be all Indonesian or?
Mostly Indonesian. I think
Okay.
Indonesian. All of them are Indonesian as far as I know.
Mm-hmm.
No intercepting people from US or English. No English people.
Okay. I'm not sure if I can finish in 40 minutes. I'm a little worried about the length of the pages, so I will do my best to finish in time. Subchan, your sound is turned off.
Sorry, yeah. Some of participant actually is lecturer, senior lecturer.
Okay.
So it's fine. Don't worry about that.
Mm-hmm.
Some of us later will be speaking in Indonesia, maybe Prof. Kim. So we will use maybe bilingual.
Okay.
Because maybe some student doesn't understand, and maybe they will ask in Indonesia, and we will translate it for you if you have to answer it later.
Okay. Okay. But if I don't understand, you can type in the chatting window. Okay.
Okay.
Sometimes I cannot hear very well because of the network situation.
Okay, I think because have you mute your okay, now it's fine. I think is it fine? Only one people. I mean all the member in my meeting room already mute the sound. Is it fine now, the sound?
Okay. Is there
The
any
voice.
echo from my speaker?
No echo. It's fine.
Okay.
Okay.
So how about the length of you guys' presentation?
Oke, good morning everyone. Selamat pagi Bapak Ibu semua yang sudah hadir di acara kelas Profesor. Nah,
Okay.
ada.
Sing a song.
Sorry, Prof. Kim, there was a sound from children.
Totally okay, no problem.
Yeah, all participants later will be muted anyway. Don't worry. At this time, maybe it just started. Sorry if I speak in Indonesia later to let them. Maybe in the opening speech I will speak in Indonesia, Prof. Kim.
Okay, no problem.
A little bit translated in English as well.
Nanti biasa aku share
Kalau nggak follow berarti
baca
malah
aja
satu.
dulu ya.
Iya benar.
Dibuka kelas mana? GM profesor ini. Tapi saya orang dulu nggak setuju. Kalau saya mah
Oke aja ya.
pertama sistem orang Jepang. Orang Jepang itu nggak pernah nunjukin dia pintar, diam aja. Tapi dia yakin dia bisa. Kita jangan nunjukin oh gue bisa loh, tapi kita yakin kita bisa. Udah nunjukin itu namanya.
Iya, kegiatan kita satu dua nomor. Pokoknya nanti kalau saya nanti dulu.
Tes. Masuk ya masuk. Assalamualaikum warahmatullahi wabarakatuh. Good morning everyone.
Good morning. Good morning.
How are you today? It's good. Okay, welcome to workshop series of applied mathematics and computing science. I am Amirul Hakam, lecturer in Mathematics Departemen Institut Teknologi 10 November Surabaya, and I'm so delighted to see you even on screen. And I will be your moderator in this workshop. Before we get started, I would like to remind you about the rule in this workshop. The first is please use format name in your Zoom account. It can be your institution following your name. And then turn off your microphone during the presentation. And if you have any question, You can type on Zoom chat box, or you can use raise hand facilities in Zoom. And I would like to read the sequence in this workshop. There are 4 sessions. The first is opening, and the second is presentation, and the third is discussion, and the last is closing. For the opening session, I would like to invite Mr. Subchan as a head of Mathematics Department of Institut Teknologi 10 November Surabaya to give the speech. For Mr. Subchan, please, time is yours.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone.
Assalamualaikum warahmatullahi wabarakatuh.
Prof. Kim, as I would like to say thank you very much for Prof. Kim, who is our wood class professor for this meeting. It is our honor to have you with us. And also thank you very much for Mr. Dieky, Ibu Mrs. Tahiyatul Asfihani, another speaker from Indonesian side, fortunately from ITS at this time, and all the committee, organizing committee for this meeting. Thank you very much. And also to all participants today, thank you very much for joining with this meeting. Hopefully will be useful for us and also blessing for us. Okay, I will speak in Indonesia a little bit. Prof. Kim, yeah, I'm sorry, I will speak in Indonesia for a while. Terima kasih saya ucapkan kepada Pak Dieky, Bu Hani, also panitia, juga pada partisipan di sini. Ada beberapa senior saya tadi itu. Ada Pak Yusuf Fuad dari UNESA juga saya lihat. Ada teman-teman dari kampus lain. Ada dari ITK saya lihat, ada dari ITS tentu banyak sekali. Ada juga mahasiswa, ada dari UNTAD juga. Alhamdulillah, this meeting is funded actually by Wood Class Professor Program. It will have around 4 workshop series on applied mathematics and computing sciences. This is the first one of this workshop. So it is very delighted for me to have all of you with us and hope you can join again in the next workshop. Mostly our workshop will be mainly in mathematics and its application. The application mainly later with the unmanned vehicle, because Prof. Kim expert in unmanned vehicle and also something else like flapping wing, which is in Indonesian side until this time. I think no one is working on the flapping wing. We are working on the robotic, also drone, but not on the flapping wing. I think only few countries working on flapping wing. But Prof. Kim will give about flapping wing later in the 3rd and the 4th workshop, hopefully. I think that's all for my speech. Terima kasih banyak buat Bapak Ibu semua yang tidak bisa saya sebutkan satu persatu. Ada dari Universitas Pakuan, ada Universitas Unram itu Samratulangi, ada UNTAD juga, tentunya ada UB, UINSA, UNED, dan banyak lagi. Mohon maaf kalau saya nggak bisa menyebutkan satu persatu. Thank you very much. Hope we can enjoy the meeting. And if you have some question on later, you can contact us at the Department of Mathematics. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Subchan, as the speech. And the second session is presentation by 4 speakers. Please, I would like to read the CV and I will share screen. Okay. The first speaker is Professor Seungkeun Kim. As a full professor, I'm sorry. In Department of Aerospace, Engineering CNU, Seongnam National University, Daejeon, Korea, and the education, Ph.D. at Mechanical and Aerospace Engineering, Seoul National University, Seoul, Korea, and Bachelor of Science in Mechanical and Aerospace Engineering, Seoul National University, Seoul, Korea. And the research project is study on flight dynamic and control of insect mimicking MAV, PI funded by ADD, Agency for Defense Development Korea, Biomimetic Robot Research Center, core technology development for automated flight of insect mimicking sub-miniature drone under 15 centimeter per 20 gram, PI funded by KAT, Korea Evaluation Institute of Industrial Technology, the development of a hybrid drone system for dual operating of flight and climbing with a duration of over an hour. Co-researchers funded by Korea Evaluation Institute of Industrial Technology, development of an SMPC flap module for moving wings. Co-researcher funded by Korea Evaluation Institute of Industrial Technology. Hello, Mr. Kim. Hello, Mr. Kim, Professor Kim.
Hello.
How are you today, Professor?
It's good. Thank you. Thank you for your introduction.
Yeah. Today, Professor Kim will be sharing with us about MPC and its application to UIV guidance for standoff tracking. And the second speaker is Mr. Subchan, Ph.D., Head of Mathematics Department, Faculty of Science and Data Analytics, Institut Teknologi 10 November, Surabaya, Indonesia. And the education, Ph.D. at Cranfield University, Defense Academic of the United Kingdom, and Master of Science in TU Delft, the Netherlands, and Bachelor degree at Institut Teknologi 10 November, Surabaya. And the research project is penelitian dasar unggulan perguruan tinggi, panduan dan kendali kapal perang autopilot untuk menghindari tabrakan berdasarkan data AIS. Hello, Mr. Subchan.
Hello.
Yeah.
Thank you for your introduction.
Yeah, Mr. Subchan. You're welcome. And the third speaker is, I'm sorry, this is typo. This is Mr. Dieky, Dr. Dieky Adzkiya, in Science Department, Mathematics Department, Faculty of Science and Data Analytics, Institut Teknologi 10 November, Surabaya, Indonesia, and education, Doctor of Philosophy at TU Delft, the Netherlands, and Master of Science, Institut Teknologi Surabaya, Institut Teknologi 10 November, Surabaya, Indonesia, and Bachelor degree at Institut Teknologi 10 November, Surabaya. And research project, formal verification of Max Plus linear system. Hello, Mr. Dieky.
Hello. Thank you for the introduction.
Yeah, you're welcome. And the last speaker, Dr. Tahiyatul Asfihani, or Dr. Hani, from Mathematics Department, Faculty of Science and Data Analytics, Institut Teknologi 10 November, Surabaya. Education, Doctor at Department of Ocean Engineering, ITS, Surabaya, and Master of Science at Department of Mathematics, ITS, Surabaya, and Bachelor degree at Department of Mathematics, ITS, Surabaya. And research project, Ship Motion Simulator and Intelligent Control for ITS Autonomous Car, or iCar ITS. Hello, Dr. Hani.
Hello, Mr. Hakam.
Yeah,
Thank you for your introduction.
yeah, you're welcome. Yes, this is for speakers today. And maybe we can start this the presentation for the first speaker, for Professor Kim. Please, time is yours.
Thanks. I will share my screen now.
Yeah.
Okay, good morning, ladies and gentlemen. Halo, senang bertemu dengan Anda.
Good morning.
Good morning. Good morning.
I'm sorry for the bad pronunciation.
Oh, no problem. Very good already.
I'm Seungkeun Kim from the Unmanned Aircraft Systems Group at Department of Aerospace Engineering in Chungnam National University. It's my honor to be here for this lecture today, and I convey my special thanks to Professor Subchan for organizing this workshop. Actually, I met Professor Subchan in 2008, so it's been 12 years now. So it's been a long time friend. Today I'm gonna talk about the model predictive control and its application to UAV guidance for standoff tracking. So I hope my lecture could be helpful for many audiences here in the domains of control engineering and autonomous systems. Okay, now let me start. Actually, I prepared 46 pages, so it's too long, but I will do my best to finish in time.
Yeah, it's no problem, Professor Kim.
Okay. This is the contents of my presentation. Firstly, introduce the model predictive control concept and brief touch on linear MPC for tracking very briefly. And then main focus of today is the nonlinear model predictive control and its application to the UAV guidance, actually 2 UAVs, and then is tracking the 1 ground target. So that is my situation. So I will introduce the nonlinear MPC concept and then define the constraints and cost performance index. And I will drive in the detail of optimal control law for discrete time systems. And then this is the main area of today is application of NMPC to standoff tracking to UAVs. I will explain briefly on the standoff tracking for this part later. So, such as background and problem definition, I need the UAV model and then ground target model for prediction of them, and then sensor model as well. And then I designed the tracking filter for target prediction. And then I will drive the nonlinear model predictive coordinated standoff tracking. It's very long, so I'm using the acronym NMPCST. So I'll show you the numerical simulations and analysis and then finish my presentation with the conclusions and discussions. Okay, the briefly MPC repeats plan for the future and do now, and repeatedly plan for the future and do now. As show, can you see the laser point?
Yes.
Yeah, so
Yes.
we're doing the planning and do now act and planning and do now at every sampling time. So actually, this is the open loop optimization because in the future time, there is no sensor signals actually. So at each sampling time, MPC solves open loop optimization problem. So for this, we need the model for prediction, actually linear system, the state space system, we can easily predict the motion of the state variable by using just the Euler integration formula. And in case of nonlinear system, in a similar way, we can predict the future state by using this nonlinear equation. X dot equal arbitrary function of nonlinear system, the function of state and control input. So we can call it the nonlinear MPC. So today I will talk about mainly for nonlinear MPC. For this, the important thing is length of predictions. So actually, however, it is difficult to do for an infinite horizon. So we will set up the prediction horizon. Actually, if we set the prediction horizon the longer and longer, it causes the computation burden, and then we cannot control the light away performance index. So the long far away performance index can be met, but the closest time cannot be guaranteed. And then we need optimizer. So actually, we will optimize the control input history only for a prediction horizon. So use U0, U1, and up to U large n minus 1. So, and then only the current control input U0 would be used. So the others will be non-used for the control. So at the next step, recursively, we can repeat the MPC scheme with sensor output and model information. So actually, we need very accurate the model information. So the dynamic equation is not appropriate for MPC up to now, because the dynamic equations involves the force and moment. So it has a lot of uncertainties from the external forces and moment equations. For example, aircraft has many aerodynamic coefficients, and it has a certain boundary. So normally nowadays MPC is generally used for guidance level, test planning, or just a guidance for making the attitude command to the UAV or autonomous systems. So I think the MPC's biggest merit is the constraints can be dealt with, such as control input saturations and state constraints and collision avoidance and etc. So I introduced briefly on the concept of MPC. Especially the linear MPC is widely used for the chemical plant process and process engineering. But normally the cost is set up as the final time, the command tracking error, and then the delta U, the control input increment, and then here is the other times the command tracking error. So actually Y equals CX. So if we have the desired Y, we can set a Y tilde, and then inequality constraints can be considered, and then control saturation can be taken into account as well. So can I use a pen? Here, this is state linear equation. So in this way, x1 equal ax0 plus u0. So we can predict very easily from previous step to the next step. And then y1 is c x1 and then next step, this is just an example, x2 equal ax1 plus bu1, and y2 equals cx2. And in this way, there is not enough space here. The x1 is here, ax0, bu0. In this way, y2 In this way, the all future state can be represented as x0 and u0. This is the current time step. So we can easily predict the future state with this linear equation. So for a linear MPC, a standard quadratic problem can be applied with control input sequence as an optimization parameter. So this is very straightforward. So in this way, we can use the collision avoidance of the autonomous cars and drones, etc. I have an experience on that, but today I will focus on the nonlinear MPC, just the nonlinear model predictive control. So I will briefly touch on this linear MPC. Now let's move on to the introduction to nonlinear model predictive control. This figure shows the overall block diagram of the nonlinear model predictive control. So there is a plant here. So plant is generally represented as this nonlinear equation in a discrete time domain. And then this is the initial condition. And then output is fed to the state estimator. And then we can get x hat here. So this NMP controller requires firstly the cost and constraints. And then secondly, the predictive model. This is very important. Actually, we have to use this equation. So this equation has to be accurate. So normally I'm using just the mass point model. This is the kinematics, not dynamics. So kinematics is very accurate. We can use for path planning or the guidance level. So optimizer can use these two elements to generate the control signal U here. So the constraints is the nonlinear discrete time dynamic system. So I will use this is equation 1. Xk plus 1 is the arbitrary function of f at the time of k and state and control, and this is the initial condition. And then another one is performance index, cost, what we want for guidance or path planning. So I will talk about later about standoff tracking. So how I set this performance index for standoff tracking. So normally it has two components. First one is the final time cost. So what we want for the final time, so what we have to minimize for the final time, this is phi, and then this is R. So other time steps cost. So this is initial time step to m-1. Actually, the last time step large n, we cannot decide the control input at the time. So normally we are separating the final time cost and the in the meantime cost. So our optimal control problem is to find control UK star on the interval from initial step to final step that can drive the system 1 along the trajectory xk such that the value of the cost or performance index number 2 is minimized or optimized. Are you guys with me? So am I fast?
Very clear. It's fine, it's very good. Don't
Okay.
worry.
Thank
Very
you.
good. Excellent.
And then I can introduce some useful performance indexes. Minimum time problem. So that can be in a continuous time. The minimum time problem normally set TF. Like this. But here, in a discrete time domain, the final time step large n could be set up the minimum time problem. So we can express as a sigma like this way. And then minimum pure problem can be set up like this. And then minimum energy problem is the final time state cost. And then in the meantime cost, x and u. This is very similar to LQR. So there is a question, what are pi and L in the previous slide here. In this case, pi is 0 and L is 1. And then here, pi is 0, L is absolute value of UK. And here, this is pi and this is L. So in this way, we can set up our what we want for cost minimization. So this is just an examples. So now let us move on to the optimal control derivation of discrete time systems. So let us define the augmented performance index, the final time cost, and in the meantime cost. And then here, this is our constraint, plant dynamics. Actually, I buy the electric pan for online lecture for our students because of under the COVID-19 situation. So I'm using now. And then let us rearrange this cost augmented performance index with a Hamiltonian function like this way. I think everybody is familiar with this notation. So except this k plus 1 state, we can set up the Hamiltonian function here. And then we can express again this equation with Hamiltonian like this. By slide manipulation here, so you can see here initial to n-1, here initial +1 to n-1, like this way, we can pull out the last term of this one, like this. And then this is the k plus 1. So if you substitute the I plus 1 here, so the initial Hamiltonian can be pulled out from inside the sigma, like this way. And then we can express the increment in augmented cost with respect to the state and control, and lambda here, Lagrange multiplier. So we can express like this way. So I will skip the detailed derivation about the increment. You can see you can partial differentiation of pi with respect to the xn, and then dxn. This is just a chain rule, as you know. And then here, there is xn, so you can add up here, and then this one and this one. This is the increment with respect to x and u. And then here, x and u as well. So you can get these two terms. And then here, you can get this increment. And then lastly, the lambda, the function of lambda here and here. So you can get these two here. Oh, it is complicated lines here. Sorry about that. So finally, we are getting this final differential form of the cost. So this cost, to be optimum, it has the minimum point. So the differential should be equals 0. So here and here and here must be 0. So we can get these three equations. And then here, this equation actually, this is the dynamic constraint, dynamic equation for plant from equation 1. And this equation is co-state equation about Lagrange multiplier. And then this equation about the optimality condition with respect to the u. And then here, there is a boundary condition for the final time and initial time. here. So for the final time, this term should be 0 to be minimum. However, actually normally our final state is normally free for optimization for our application. So dxn is not 0. So this term must be 0. So we can get one boundary condition here. And then normally initial time, initial state, sorry, this is initial. Initial state is normally not free. So initial state normally fixed. So dxi equals 0. So this is naturally satisfied. So normally we don't need to consider this kind of boundary conditions. Okay. So in summary, our system model, and this is what we want. And then this is the Hamiltonian, the mathematical tools for optimization. And then we can get these 3 equations. Actually, this equation is the same as system equation. So this is the new. So this is 2 new equation. But here, as you see, lambda k is expressed as function of lambda k plus 1. So we have to backward integration in time, like this way. And then this is a stationary condition. And then this is a boundary condition. So this is the short summary of optimal control of discrete time systems. So now we can apply this discrete time system optimization to the receding horizon control, model predictive control, other name. So in the limited time sequence, we can apply this kind of optimal control of discrete time systems if we properly set up the dynamics in discrete time domain and what we want, the cost. Before going to the Standoff tracking application, I will introduce this book and this website. So actually, this is not my book, but this is very good for first-time user of the nonlinear model predictive control. If you go to this website, you can get the nonlinear model predictive control routine, the function, and then there is examples here. So that is very good. And then if you see the nmpc.m, if you download, you can see this affirming con is used. Affirming con is function minimization with constraint. This is MATLAB function inside the MATLAB function. So you can easily set up the cost and constraints. So this one is very useful for the first time developer with nonlinear model predictive control. So I'm just introducing this website. Actually, I didn't use this function for my application, but the first time user can use this kind of the toolbox. So now let's move on to the application of the Standoff tracking for UAVs. So firstly, I will talk about the background and problem definition. Can you see this movie clip? So there are 2 UAVs, and then there is one ground target here. So it shows stop and go, and then envelope turns. So its acceleration and velocity is changing. So UAV, it is difficult for UAVs to track properly the kind of the ground target. So I assume the 2 UAVs can track this ground vehicle, a car. So there are 2 what we want. Standoff distance keeping. So I want to keep the distance from the target to the UAV, RD. So in my simulation is 500 meters. And then another one is antipodal tracking. So the 2 UAVs, one is here and one is here. In the case, 2 UAVs can monitor the both sides of the car. So maximize the monitoring performance. But sometimes the 90-degree can be used for some target. So it can see the left side of the target, and then it can monitor the behind the car. So in my case, in my simulation, is antipodal tracking is another the performance index. So I have to minimize the relative phase angle between two UAVs as 180 degree. So that is my optimization performance index. And then the main performance index is keeping standoff distance. So aim of this study is applying the model predictive guidance, because the predicting the ground target trajectory will be very helpful for UAVs, because we can predict the trajectory of the car, so the UAV can move in advance before the movement really happening. So the UAV can move some to the certain point in advance. So, and then another merit will be optimal performance. Normally in the literature, everyone is doing separately control the turn rate and speed. As you expect, to keep the antipodal tracking, the UAV1 is faster than UAV2. UAV1 have to decrease their speed, and then UAV2 have to increase its speed. So normally speed control can be done for antipodal tracking. But however, that is related to the standoff tracking distance performance as well. So I wanna do by coupling these two control elements by using the optimal control. So UAV dynamic model is just simply, this is the point mass model, x dot equal v cosine psi disturbance, and then psi is heading angle and velocity and rate of change of the heading. So there is some delay in the control loop. So I assume a small delay inside the control loop. So this equation can be described by just the Euler integration, like this way, using sampling time. And then there is some control input saturation setup here, the inequality constraint. And then for realistic situation, I designed the tracking filter using Kalman filter. So although ground vehicle generally move with the lower speed than aerial target, they irregularly stop and go and stop and go with a small ready. So I'm using the traffic simulation program. So it is observed that jerk is the differentiation of the acceleration. Jerk is not negligible, but acceleration is piecewise constant. So acceleration dynamics can be applied to moving ground vehicle. So this is the acceleration dynamics proposed by these guys in 1997. So I'm using this as a tracking model, as a target model. And then the process noise of the target acceleration characteristics can be set up as shown here. So you can see their paper about the tracking filter, the linear model. So I'm skipping the detailed explanation. And then let's move on to the sensor model. So I assume the UAVs is carrying radar. So moving target indicator radar to localize the position of the target normally, but they are not sensing the directly position. So their measurement is here is the UAV and the target here. So they are sensing to the, they are sensing to the heading angle azimuth, and then distance r. So our measurement is the relative distance and then the relative heading to the target from the UAV. So this is nonlinear. So we have to apply the extended Kalman filter here, and then noise covariance matrix we can set up like this way. Are you with me? Okay.
Yes, yes, yes.
Now let's move on to the tracking filter. So I applied the extended Kalman filter because the MTIR's measurement equation is nonlinear, as I said in the previous slide. So this is normal time update equation and measurement update equation. So, and then we need HK here that can be obtained from the linearized Jacobian of the nonlinear measurement equation. So you can derive like this way. And then the problem is there are two UAVs. So they can do tracking filter separately. So by using some communication, state vector fusion can be done. The sensor fusion can be done. So as known as track fusion, we can combine the two filters outputs, one UAV or I'm considering the decentralized way. They are exchanging their own, the filter outputs each other. So in each UAV, we can do this kind of the state vector fusion. That is this one and this one. This is the UAV one. This is the pair UAV. So we can exchange the state estimation information through communication. So we are assuming the communication bandwidth is wide, enough to transmit state 6x1 and covariance matrix. To be 6x1, x, y, and x dot, y dot, x2 dot, and y2 dot. So that is 6x1. Position, velocity, and acceleration. My tracking filter is composed of that kind of state. So 6x1 and 6x6 covariance matrices must be communicated with each other. So instead of the state vector fusion, the information filter can be used for minimizing the communication load. And then this equation will be used, the initial condition for target trajectory prediction of MPC with the time update equation of extended Kalman filter at each sampling time. So I will use this extended Kalman filter and state vector fusion as the prediction model of the target and then initial condition of the target. So let's move on to the nonlinear model predictive coordinated standoff tracking. Okay, this is the main part. So up to now, this is just the introduction about the discrete time system optimization and setup for my application. So this is what I want. The basic aim is my algorithm is to find the control input sequence, minimize the following performance index. This is final time, and this is the cost in the meantime. Just initial to the just before the final time. So my aim is word 2. First one is standoff tracking, distance keeping here. This is R tilde. And then D tilde is the antipodal tracking, the keeping relative phase between UAVs. But however, if you use the angle directly to the coast, there will be some problem. Because the heading angle difference has some the bad behavior at the boundary, the pi and minus pi. So I'm using this kind of relation using the inner product of the two relative vectors. I will explain it at the next slide. So here, RD square minus R vector is here. So that means R vector becomes RD. The standard tracking distance keeping can be obtained. And this one will be explained later. And then this is the final time cost. And then this is the cost in the meantime. And here, this is the control input saturation. To minimize the control input, sorry, not saturation. This is the control input U minimize. So this is the energy minimized term. So this is what I want, and this is the U minimization. Control input energy minimization. And then here, large N is the length of the receding horizon. So in summary, if you apply this kind of the cost, you can get some tipping distance from the target from UAV, and then UAV has to place keeping 180 degree each other. This is why I'm using the kind of the cost for antipodal tracking here. D tilde is derived from the inner product of RK and RK pair. So it's target and UAV1 here, and UAV2 is here. This is RK, and this one is RKP. So if you wanna 180 degree this between these two vectors, so this one becomes pi. So this is very simple. So pi, that means this is -1. So if you move this term to the left-hand side, you can get this equation. So if you minimize this left-hand side square, you can get antipodal tracking. But this is very efficient for using the angle difference. And then there is some normalization problems because the standoff distance keeping is matters, and then antipodal tracking is degree or radian. So there is some gap in the physical dimension. So I'm using this kind of technique. And then this is dynamics of UAV. And then there are two equality constraints. First one is control input saturation. And then this one is the collision avoidance. Between two UAV. So two UAVs distance should be bigger than some safety distance. And then this one is the normalization term. So I wanna all the inequality constraints keep inside the size of the one, the vector size, the lower than one. So that is the normalization term. So let us set up the augmented performance index defined by incorporating equality and inequality constraints. Here, this is the system equation. And then this one is the what I want, the cost, standoff distance, and antipodal tracking. And then this one is control input saturation, and this is collision avoidance, inequality constraints. I'm using here R, here and there, like this way. This makes the inequality constraints applied only when they are violated. To facilitate the derivation of optimal control law, let us define a Hamiltonian in a similar way, like this. And then, in a very similar way, you can get the variation, like this, as I explained before for the general case. And then you can get these two conditions. this is actually slide number 10. This is final time boundary condition. So you can get this equation and then variation of JA. So if you, oh, not here. If you use this and there, you can get 0, these two terms. So we can get this final variation of cost. And then here, we need some kind of partial differential equation for partial pi, partial xn, and partial hk and partial xk. So I derived this partial differentiation. That is very easy. Looks complicated, but if you do, you can get the derivation in the same way. And then finally, we can select the duk like this way. And then if you substitute into the dja in the previous slide, you can get this type of equation. So this is always decrease this sign. So if you apply this kind of duk, the cost always can be decreasing. So control input can be updated in this way because duk is here. So next time UK is decided by using this kind of relation. So if you want to do this, you have to drive some kind of the partial derivation, partial differentiation about UK and about system dynamics. So this is straightforward. Okay, sorry about many formulations here. So this is my algorithm summary. So here, this is UAV 1 and UAV 2. By using communications, they are doing separately measurement acquisition from radar, and then target localization and sensor fusion here, and then communications, and then target state propagation and pair UAV state propagation. So we need other UAV's future position and target car's future position. We need that. And then optimization, what I showed up to previous slide can be applied in this way. Lambda and augmented cost and self-state propagation. Self-state propagation means its own propagation using the dynamic model. So in this way, the decentralized structure of online optimization can be applied between two UAVs. Finally, now I'm moving on to the numerical simulation and analysis. Are you okay?
That's okay.
Yes.
Yeah. So I used the trajectory data from S-parametric traffic model of device. This is Malaysia in the UK. This is a position measurement with respect to the UAS. So start from here, goes into the town and left turn and right turn and in the marketplace and goes out to the northern eastern side. So this is the end of the car trajectory. So I assume the two UAVs is tracking this ground target by using optimization. So measurement noise like this way. And then I need some comparison. So the previous technique proposed by the US professor, that is the reapproach vector field guidance, that is very simple. So I compare with this simple guidance algorithm. with my optimization technique. And this is the simulation parameter. Here, theta desired, this is the pi, antipodal tracking between UAVs relative to the target. And then here, this is standoff tracking distance, desired value, 500 meters. And then collision avoidance safety distance is 30 meters. And then prediction horizon is just a 4-step. Because this is 2 Hz signal, so that is equivalent to the 2 seconds of prediction in the future. So that will be very helpful to the UAV guidance because the ground target is predicted to the 2-second future. So we can make the UAVs act in advance relative to the future the target movement. This is the simple result of my simulation here. It looks similar, but when the target doing the right turn or turning abruptly, the standoff distance tracking performance is better than the previous guidance because the NMPC is propagating the prediction of the future state of UAVs and car trajectory. Do you agree? it looks very similar, but let us see some graph. Now this is the Kalman filter estimation. So this is jittered signal is the sensor signal combined with the sensor noise, and then this is the dotted line is true, and then green line is estimation by extended Kalman filter after sensor fusion, after communications. And then this is the absolute trajectory of 2 UAVs. This is the reapportant vector field case, and this is my case. As you can see, the 2 UAVs relatively some kind of the tracking behavior because the ground car moves in a right turn and left turn like this way. This is the relative movement of 2 UAVs. Can you see the difference? So this is the standoff distance is not well maintained here, and here. So the deviation is much bigger than the optimization scheme. So if you apply this kind of the predictive control, the deviation to the standoff distance keeping is very low. And then this is the distance, relative distance to target, UAV 1 and 2. So this deviation is smaller than the previous case. And then this is the antipodal tracking performance. To keeping the 180 degree between UAVs with respect to the target position is almost similar than the previous case. So the conclusion is that keeping the antipodal tracking performance is very similar to the previously proposed guidance scheme, but the standoff distance tracking performance can be much better. So this is the speed command on UAV and turn rate command on UAVs. So if you see the numbers, the mean standoff distance error here is getting much improved compared to the LVFG, reapportant vector field guidance, and phase keeping error is almost similar. And then control consumption is a little bit similar level. So that means the model predictive guidance is using same level of control but you can get some optimized performance in the standoff distance keeping. So phase keeping performance is similar level, and then this is the computation time on the model predictive control at every sampling time. Actually, the 0.5 second is the sampling time, but the computation time is 0.1. That is 6 years ago. So nowadays the computer is much getting better. So I think it takes shorter than then. And then in the embedded system can do it now, I think so. Yeah, it takes 1 hour. I'm sorry for the long time presentation. Yeah, this is my publications. So actually, this one is the Journal of Guidance, Control and Dynamics paper. So you can refer to this paper in detail about the NMPC. And then the others is about the standoff tracking or application of the model predictive control.
Hello, Prof. Kim. Maybe Prof. Kim get disconnected.
Just wait for a while. While waiting.
Hello?
Hello, Prof.
Hello, hello.
I think there was some connection problem.
So I was kicked out from the from the Zoom. I'm sorry. Our network fault?
Yes, it's look like from Korean side, I think.
Okay. I'm so sorry about the problems. Oh, anyway, yeah, my conclusion is the model predictive control can be applied to the UAV guidance more than 2 members for not the inner loop control, not attitude control, but in the level of guidance, position keeping, or the commanding to the next waypoint, etc. That can be easily applied to the high level guidance. And then or the path and action planning of autonomous systems. So only if you can set up the proper proper cost, what you want, so you can easily apply it to the MPC. So nowadays MPC is widely used, especially linear MPC in the industry. The industrial guys thinks the MPC is the most useful control techniques for their future, but in the autonomous systems and aerospace domains, up to now, it is still difficult to apply this MPC scheme to the inner loop controller. So I think so because there are much the uncertainties in the dynamics. And then aerospace is always flying, so if you fall off, if it is falling off, it can be a big problem. Anyway, thanks for your attention so far, and I wish all your health under this COVID-19 situation. Actually, the Korean situation is very bad. Actually, nowadays, getting getting bad. Thanks for your attention again.
Yeah, thank you, Professor Kim. Okay, before we go to the next presentation, maybe we want to take a picture together. Yeah, Mr. Subhan. Please, everyone, you can turn off your video and we want to take a picture. And I'm sorry, I won't stop your screen, Mr. Kim, Professor Kim.
Okay, I will stop the sharing.
Yeah.
So we want to have picture together, Prof. Kim.
Okay, no problem.
For us.
Online
Okay, I
picture
mean
taking.
participant. Yeah, that's celebrity from Korea now. We have celebrity from Korea.
Okay, and I will count for five times. Yeah. And the other, please turn on your video. Okay. Give your smile. One. And two. Three. Four. And five. Okay, thank you so much. We can go for next presentation. It's for Mr. Subhan. Okay, for Mr. Subhan, please, time is yours.
Okay. Thank you very much, Mr. Hakam. Thank you very much, Prof. Kim, for your presentation. It's very interesting and it's related to the second presentation, actually. It's very, very related. So I don't need to explain my control law now. And I don't prepare for that, actually, anyway. That's good then for me. Okay. I will share my screen now.
Yes.
Yeah.
Okay, can you see my screen, guys?
Yes.
Okay, very clear, yeah. Okay. Just a second. Okay, thanks a lot. I think the participant is now is about 100 participant. Yeah, maybe some of the student having class, or I don't know, maybe some still 100 participant at this time. And thanks a lot for following this workshop. Okay, I'm going to talk a little bit about computational optimal control. I call it review and progress at this moment. I'm from Optimization and Control Group, Modeling and Simulation Lab, Department of Mathematics. This is my talk. It's not much actually, but because the time actually is for Prof. Kim, the keynote speech, I'm only 10 minutes under 20 minutes speaking at this time. So what I'm going to do, because most of us is mathematician in this meeting, I'm going a little bit to explain about mathematical system theory. I'm sorry, typo over there. Mathematical system theory, which is related to Prof. Kim control and finally optimal control. But most of them I will explain very, very briefly. So what is mathematical system theory is? I think in ITS, mathematical system theory is one of the course, one of the subject in my department. That's why it's fine for ITS student, but for other university, maybe it's not part of the course. So mathematical system theory is concerned with the study and control of input-output phenomena. This is a very simple, yeah. We have a part of mathematics actually, which is working on mathematical system theory. This one is not electrical or aerospace. Actually, in mathematics itself, we are studying in deep of mathematical system theory, where inside you know controllability, observability, and so on. And the main thing in mathematical system theory actually is the system itself. What is system? You know about the COVID-19. Malaysia now is, let's say, free from COVID-19. I call one of my colleagues yesterday that they are having life normal. They go to the office normally. While in Indonesia now we are still working from home, some of us. So system can be defined based on set, cause, or an effect relationship. Cause mean in this case is like input, and effect here is like output that can be decomposed into subsystem and applied of a restricted application domain. So system actually is discussing about input, output, and also a system itself, subsystem. I will explain in the next slide a little bit. And applied of a restricted application domain. Let's say if some of us having allergic to seafood, and our body, let's say our system, then people having allergic to seafood, they will have problem if she or he eating seafood. That's cause us the input as seafood, and the effect is allergic. That's an example. So the definition here from Professor Seungkeun. Here is the definition from Olsder. He is my professor from Delft University of Technology. So what is actually system? System is part of reality, which we think to be spirited unit within this reality. See here, can you see my see here is the surrounding area, and here is the system itself. So a system is part of reality. Outside all of here is the reality, and which we think to be spirited unit within this reality. So there is interaction between the surrounding area and the system itself. As I mentioned to you, let's say when people having allergic to seafood, then they will have problem if you give some seafood to the person. And on the right side here, we have some standard input and output on the system. So this one is simple system, as Prof. Kim already mentioned a lot before. Oh, sorry, what should do then? Nextnya gimana ini ya? It's nothing, it's not working. So I will stop share a while, yeah, because I've got a problem with my just a second. I couldn't make a slideshow at this moment. Okay. So can you see my slide now? Yeah. Can you see my slide about rain? Okay. Okay, what happened is here is an input like rain or hujan in Indonesia has an influence on the level of the water in a lake as the output. So this one is simple. If you have car, there is an input as a wheeling drive, and also the output is the performance of the car. That's another example of a system, very simple one. So in most cases, a phenomenon is studied indirectly through a model. You see, if we have modeling like what Prof. Kim mentioned before, it is not directly we apply the UAV real one, but we are doing simulation first. But in the simulation, we have to do some model representation of the system. That's presented often in mathematical terms of what are felt to be important feature of the object or system. Because if we model mathematical thing, usually it's not really the model, the real one, but we make some simplification. That's why we mention here the important feature of the object. There is important feature, not all the features, but only important one. Then we can make a model. That's why there is some error. It's similar as what we have in the real one, but it's very close enough. Okay. Now we are coming to the navigation, guidance, and control, which is part of mathematical system theory, as Prof. Kim explained a lot already actually. What is navigation, guidance, and control? Usually three of these words mix up together. Actually, what is navigation? You see, when you want to go to some destination, usually you pick up your smartphone and you define which city or which position you want to visit. This one is part of navigation. It's process of establishing the location. So navigation itself, actually, based on my book, is the process of establishing the location. Then what is guidance? Based on the location, if you go to Google Map, when you have initial position and final position, then they will guide Google Map from which initial and which final trajectory will follow the desire. So the guidance actually produces the trajectory needed to be followed. So navigation, guidance. So you have a position, and now we have a like list of points that we should follow. Then finally, control entails the use of actuators so that the desired trajectory can be followed. I'm going to explain a little bit in Indonesia. I'm sorry, Prof. Kim ya. So what is navigasi? Kadang kita mix up ya, mencampurkan kata-kata navigasi, guidance, and control. Actually, navigasi adalah menentukan posisi. Kalau kita mau pergi ke suatu tempat, maka kita harus menentukan tempatnya, lalu di mana kita berasal. Kalau kita buka, when we open Google Map, and we use the facility of Google Map, then Google Map will give you trajectory, will give you point where we should go. Then, how to go from initial to final with the guidance, we have to use control. It's very clear, yeah? Okay, I will use English again, not bilingual now. So, what I'm going to do today is going to give you an example of control problem. It is simpler than Prof. Kim because this one is open loop one, as I use in my book. So we have terminal band maneuver. What is terminal band maneuver actually? So when we want to hit a target by cruise missile, what we want to do actually, we want to destroy from above. The missile should should finding the target from above. Struck is how to say, struck is destroying coming from above of the target or 90 degrees from the target. That's why we call it terminal band maneuver. So in this case, let's say I want to hit the bunker, where the bunker itself usually is not clear, is under the surface of the earth, is hidden on the ground actually. That's why we have to hit the target from the above. So in this case, the action of the approach is to compute an optimal trajectory together with the associated control. In other words, for a given launch and strike condition, find a missile trajectory which hit the target in predefined way, shapes the missile flight in the optimal fashion, define the control demand for optimal path. So you can imagine if I want to launch a missile from, let's say, from Surabaya to the middle of Java Sea at the center over there, what I should do, I have to define the target as I mentioned to you in the navigation and where I have to start. Then I want to hit the target from above 90 degrees to the surface. So, and I mentioned here as well for given launch and strike condition. Sorry with my English, somehow it's Japanese English, yeah. For given launch and strike condition. What the given launch in this case and strike condition? So in this case, somehow to avoid the sensor, to avoid the sensor from satellite or something else, we have to keep the missile as low as possible flight. Jadi kalau kita, sorry I speak in Indonesia now. Jadi saya ingin menembak atau menyerang sebuah kapal di tengah Laut Jawa at the middle of Java Sea. Then what I should do actually, I have to use my missile flying as low as possible. So when it close to the target, of course, the missile should flying up and down because I want to have 90 degrees to the surface. That's the given launch and strike condition. So this one can be expressed, sorry, in this term. So this one is the dynamic of the missile. Maybe it's slightly different with the normal one. So I have the objective function. Here is the objective function. I want to minimize H. If Professor Kim discussed in discrete, I want in continuous at this time. So H here actually is height or the altitude of the missile, ketinggiannya. Jadi I want to minimize the altitude along the trajectory of the missile. With the dynamic of the missile, actually we have a fly path angle, as you see here, T minus D over mv sinus alpha, and so on. And the speed itself also, can you see my mouse here? Okay, so, and the speed as well is composed from the derivation of this system, of the figure, while x here is horizontal position and h here is the altitude of the missile. So I want to minimize the altitude of the missile with some certain launch and strike condition. So this example actually based on my book, which is on computational optimal control tool and practices. I don't explain this one, yeah, because Prof. Kim already mentioned it more detail from continuous to discrete. That's why I don't explain again about optimal control. It's similar actually to find an admissible control U, which is on this Lagrangian term, which minimize the objective function like this. And we have some constraint. In this case, I give very complete constraint. Let me explain a little bit here. We have the dynamic of the system, which is the missile, in my case, at the previous slide. And we have initial condition, usually known. And here we have final condition. And we have mixed control and state constraint. And also state constraint. Let me explain a little bit in the control constraint here. I think it's normal in the physical interpretation. There is a maximum power and minimum power, or maximum angle or minimum angle on the missile, let's say, or on the actuators of the missile. And S itself is the state constraint, usually, which is very difficult in this case to cope with the state constraint, because the state constraint parameter is only a state without control. Okay, this one is the little bit theory, and this one is the problem. And this one is not a simple problem because the component inside the dynamic here having very complicated term. Let's say the drag here, D is the drag, and drag force as well we have, and also normal aerodynamic force L here as well. It depends to the coefficient of lift and the wingspan of S reference as well. And here the air density of the area. And we define as well the initial condition and final condition. And how to solve this problem? Sorry, before that, I explain a little bit about the constraint as well. As I mentioned before, we have state path constraint, which is the speed of the missile is not as easy as we think. They have minimum speed or maximum speed. What does it mean actually if we have missile? Let's have a look. Let's say when we drive a motorbike, when our speed, let's say 200 kilometers, not like the motor GP, yeah. Let's say when we live in Seoul or Chungnam, or let's say in Surabaya, we cannot drive 200 kilometers per hour. Otherwise, our motorbike will broken. And we drive very slow, let's say less than 10 meters kilometer per hour, then they will have a problem. We will fall down actually because it's too slow. Unless you walk with your motorbike, that's less than 10 kilometers per hour. That's why this one is realistic. And we want to minimize as well the missile altitude as well. The minimum, what does it mean? If the missile, let's say, flying under 5 meters, it will destroy the house. The house is along the trajectory. In this case, we keep greater than 30 meters, let's say. Let's say in the city it's impossible because we have highest building, then impossible to use 30 meters. And of course, we have thrust, normal aerodynamic as well in this case as a mixed state and control constraint. And how to solve this problem, optimal control problem, with all of this constraint, as Prof. Kim mentioned, and I don't need to explain again. Actually, we have to define Hamiltonian, as Prof. Kim mentioned before. We have H here. I make it simpler. We have Hamiltonian. We have the Lagrangian part of the objective join of our dynamic system. Then, of course, we have some 2-point boundary value problem. See, here is the stationary condition. We have to take a first derivative of the Hamiltonian with respect to all the controller and equal to 0. Then we have, after that, the U itself substitute to the Hamiltonian, and we have to take x dot and lambda dot as state and co-state equation. And here, as Prof. Kim mentioned as well, is the boundary condition. It's simpler than Prof. Kim actually, because he translated to the discrete one. So, you know the problem. We want to minimize the altitude of the missile while we want to hit the target from above. So, I will give you some result now. See, here is the result. Oh. See, here is the result. I'm sorry, I put it here, the time below actually. So the missile, when we launch at 30 meters altitude, the missile will fly as low as possible. See the final speed. You know, when we hit the target with higher speed, then we have to maneuver a bit earlier, flying above and down a bit faster here. See here, if I want to hit the target, VTF here, sorry, if not clear. VTF is the speed at the final. The missile have to hit this target at this different speed. See here, for speed 310 meters per second, the missile should take a position a bit earlier, flying up and down a bit higher, because we have to take, let's say, position. I mean, in Indonesia, we have to take apa itu ya kalau di bahasa Indonesia ya. In Indonesian, we have to take ancang-ancang. Yeah, what is in English ancang-ancang? Position ya, ancang-ancang ya. So we have to take position because we have to hit a target a bit faster. See here, the component of the flying is very interesting. As we want to hit the target from above, then the missile itself flying very low to avoid the satellite detection, to avoid detection from some sensor or something else. Is it clear? Yeah. So in this case, the missile flying very low, and then when it hit the target from above, when it's close to the target, the missile flying up, and when it's physically can hit the target with the certain speed, then they will hit the target a bit faster here. See the time here as well for 250 meters per second is a bit faster than 270 or 310 in this case. This one is the figure of the trajectory of the missile. It's look very simple, but here is the angle of attack, and here is the thrust, both of the controller of the missile. See, it is very, very difficult in this case because we have a jump condition in this case. Let's say T1 minus in the case of 270. We have a jump condition, while for the discrete time, because this one I use actually direct or indirect method. Later I will explain a little bit in the final presentation. Then the angle of attack is directly very low, because they have to dive to the target. Well, when it close to the target, then they increase the angle of attack again. The interesting one actually in the thrust, you know, when you are driving in the 60-degree slope, or no, too high, 60 degree, let's say 30-degree slope in the mountain, then it will getting slow. Okay, the moderator mentioned to me still 5 minutes. Hopefully I will finish soon. See here, we have, for the case of 250 final speed of the target, the missile fly using full of the thrust till at the top of the trajectory. If I come back to the previous one here, in the top here, they still use maximum thrust. Just before that, it's give switching to the minimum thrust. Why it's switching minimum thrust? Because they have to turn down from up. Now it's diving. That's why it's physically correct that the missile should turning the thrust, let's say make it slower, then diving, when it dive, it's coming up again to the maximum thrust. Why it come to maximum thrust? Because we need to hit the target very fast with certain speed. Okay, this one is the comparison between some of the computational software. In this case, I use Derivation, which is based on the direct collocation. Promises and SOC, as far as I remember, using transcription method. It's similar actually. It's not direct method. It's not indirect method as we discussed. But here we use, as we discussed, we use indirect method using Hamiltonian. But in this case, we use direct method. So here is the performance of the flying between 310, 270, and 250. See the difference. We have level flight, level climbing. I mean, in this case is flying up or climbing, memanjat ya in Indonesia. And finally, we have diving. And H here is the altitude, and thrust, and L is the normal aerodynamic force. So, because my title is about computational tools, computational optimal control, I would like to mention here as well, there are so many computational tools, especially in the open loop case, like what I did, different with Professor Kim did, yeah, is doing research. My research at this presentation is using open loop. We have a DIR call, GSOP. The simplest one actually is BVP4C, which is available on MATLAB, like FMINCON, as Professor Kim mentioned. BV boundary value problem 4C here is developed by Prof. Lenhart from Tennessee University, US, if I not wrong. And we can use as well forward back Rankata as well. It's based on the book of Prof. Lenhart as well. Dido is from Naval Postgraduate School, and BND SEO, which is only one in this list, which is using indirect method, which is using very sophisticated code. Because what we can do for this BND software, we have to give very close approximation to the trajectory. So I would like to close my presentation. That's based on this presentation, presentation. We have some tools to solve our open loop control. It's quite a lot here, as mentioned to you, and some of them having a good and bad. That's why we have to try. And in my department, we use mostly BVP 4C and Rankater at this time because we don't have a license at this time for some of the commercial software. BND-SEO is free, but it's quite difficult to use. I think that's all for my presentation. Thank you for attention. I give back my time to moderator, Mr. Hakam. Thank you, Pak Hakam.
Yeah, thank you, Mr. Subchan, for great presentation. And we go to the third speaker for Dr. Dieky Adzkiya. Hello, Dr. Dieky.
Hello, Pak Akam. Thank you.
Yeah, for Dr. Dieky, the presentation time is yours.
Yeah, thank you. Let me share my screen first. Okay, can you see my screen?
Yeah.
Yes, clear.
Yeah. First of all, thank you for the opportunity given to me to give a presentation in this workshop series, which is a part of WCP, World Class Professor Program in 2020. In this presentation, I will present some materials in the topic of formal verification. So formal verification is a little bit different from systems and control, which is the main topic of Professor Kim and Pak Subchan that has been presented previously. But recently, formal verification is also can be used to design a controller for some systems. So formal verification is quite new compared with systems and control because formal verification is invented around 1990s or 1980s, something like that. So first I will give some historical background behind the motivation of why we need such method. So there are some examples where some bad things happened in the past. The first example is about Intel Pentium. I think we know that this is one of the famous processors for computers. And in this case, there were some mistakes in the computational part of the Pentium 2 processors, and it cost $475 million to replace the faulty processors. There is also another example. So in the airport, when we go to another country by using airplane, then we usually put a big luggage. So in the airport, there is a system to drive the luggage from one place to another place. And this is the example in Denver Airport. And in the past, there were some errors in the, or some problems in the Denver Airport, and the cost is $1.1 million every day. And the problem remains for 9 months. So it caused a huge loss for them. And then the next example is about the online system for booking air flights, as we usually use when we book flights. So when there is an error, when there is a problem in the online ticket reservation system, then the company may bankrupt because of this, because they have to give some compensation to their customers, and it takes also a huge loss for them. And then the next example is from the launch of missile, airplane missile that goes to the moon, Ariane 5, which was launched in June 1996. It was crashed 36 seconds after launch, and after they investigated the reason, it was because of the conversion from 64-bit floating point to 16-bit integer value. And this is also another example. So this is a medical equipment to give radiation therapy to the patients that have some cancer problems. The name of the machine is Terak 25, and between 1985 and 1987 there were some patients that was died because of overdose of radiation. So the amount of radiation is too much, so that it they were killed because of that. So from the examples that we just discussed, so we know that there is a problem. So there is a problem in the stage of when we want to decide whether a prototype or a model is good or not, whether the model or the prototype satisfies our requirement or not. So in the past, when we want to check the design or the prototype, we use testing or simulation. So this is the early method that we use when we want to check whether a prototype or a model satisfies our requirement or not. We simulate or we test many times, like 1,000 times or something like that. If the number of problems is quite small, then we conclude that the model or the design is okay. But however, when there is no problem at all, then they conclude that okay, it is, then we can produce the equipment and sell it to the market. But however, this is not true, because when we do 1,000 simulations and there is no problem at all, we cannot conclude that the design is okay. We cannot conclude that the design satisfies our requirement or our specification, because it may happen that in the next simulation the problem will occur, and in many cases we cannot do simulation for any possible situation, because the number of possible situation is too much. So we cannot try all of them. So then this is the motivation why we need a technique called formal verification. So formal verification is basically we have a model, we have a mathematical model, It can be linear or non-linear, as discussed by Prof. Kim or Pak Subchan. And also we need some specification. We call it formal specification. This is something that we want. This is something that we desire. We want to check whether the model satisfies the specification or not. So this is our requirement. And the result of formal verification, there are two possibilities. Either the model satisfies the specification, or the model does not satisfy the specification. And if the model satisfies the specification, then we can guarantee that all behavior of the model will satisfy the specification, because in formal verification we do it formally. We prove it in some ways. So it is a little bit, it is different with simulation, where we cannot guarantee that the model satisfies the specification. So this is the main advantage of formal verification. So there are many ways to do formal verification, and the some ways are by using model checking and also deductive verification. Model checking, the first way, the first approach of formal verification, model checking is used by automated technique. So we design a procedure, or we design an algorithm to check whether a model satisfies a specification. Because we design an algorithm or a procedure, so it will be implemented in a computer programming language, and because of that, it requires that the number of states, or the cardinality of the state space, is finite. And then the method will check whether the model satisfies the specification or not. The software that can be used to model check, to use in model checking, is usually called model checker. There are many software for model checker, such as Steam and NumSMV. And then the other method is by using deductive verification. In deductive verification, we use mathematical proof. We use proof. So because we use proof, so in deductive verification we can also use a system that has infinitely many states, because we can also prove for such systems. The proof can be done manually by using some theorems or lemmas from the literature, but it can also be done by using automated theorem proving that has been widely used in artificial intelligence. We can also use such tool in this case by formulating the model and also the specification properly. And okay. Yeah, so this is the schematic view of the formal verification. So as I mentioned before, in verification, we need a model, and also we need a specification, and then we wanted to verify whether the model satisfies the specification or not. there are two possible outcomes. Either the model satisfies the specification or does not satisfy the specification. If the model does not satisfy the specification, the model checker, the software, in some cases may give the counterexample. The counterexample is the behavior, is an example of the behavior of the model that does not satisfy the specification. So originally, formal verification was used by people in computer science. So that's why the number of states is discrete, such as in automata or transition system, something like that. But recently, it is also being used by systems and control community, like for linear systems or even nonlinear systems or stochastic systems, something like that. For mathematical model, I think we already know about it because we are familiar with it, like for linear systems or nonlinear systems. But we can also, in the literature, there are also some methods for verification that has been applied in many models, such as transition systems. So transition systems is a model that is simple, and this is the first model that is the first model where we can use formal verification because it is simple. The number of states is finite. Some people also call it automata. And then after that, some people also apply formal verification to another model such as time automata, differential equation. This is the model that we have seen in the previous two presentations. It can be linear systems or nonlinear systems. This technique has also been used for stochastic systems such as Markov chains, Markov decision processes, or Markov jumps, and some other things, and also stochastic differential equation. I myself, during my PhD, I was working on formal verification for max plus linear systems. So this is the topic of my PhD. And then there are also some methods for verifying hybrid systems. A system where there is a combination between continuous and discrete parts. And then for specification, there are many formalisms like linear temporal logic, computation tree logic, timed computation tree logic. Why do we need to define the specification? As I mentioned before, in model checking, we design an algorithm to verify whether a system satisfies a specification or not. So we need some categories because for each category, the algorithm for verification is different. So we have an algorithm to verify transition system with respect to linear temporal logic, for example. And then the algorithm for verifying transition system against computation tree logic is different. So it is another algorithm because we know that in algorithm the input has to be well defined. So we need to have some structure in the specification so that we can define the algorithm correctly. So that's for models, I think we are already familiar, as I mentioned before. But for specification, is it something new to us that is working in systems and control? I think it is not new because we know that when we have a system, when we want to design a controller, we also have some specification. We also have some requirement in our mind. For example, we want to have the steady state error to be less than 0.1%, for example. Or we want the settling time to be 5 seconds, for example, or something like that. So this is the specification. So actually, specification is not new to us. It is something that we want to we want the closed loop system to satisfy the specification. So that is some examples of specification that we usually use in systems and control. But of course, in formal verification, the type of the specification is a little bit different, but the idea is the same. We want the behavior, we want to verify, we want to check whether the behavior of the system satisfies the specification or not. So this is a simple example of verification. In this case, I choose traffic lights. So here we have several traffic lights. For example, here we have 2 lanes. The first one goes from here to there, from the bottom left to the top right, and then the, oh sorry, I think this is, no, I think this is incorrect. It should be the other way around. The other way around. So it is like this, I think. And then the second possibility is like this. So we have 2 lanes, and we have of course some traffic lights to know which lanes will pass this intersection. And then what is the specification in this case? The specification that we may want to verify is, we want to verify whether the lights in both lanes are never both green simultaneously. So why do we need to verify this? Because if the lights are both green at certain period, then the car may crash from both lanes. So this is one example of the specification that that is of interest to us, for example.
I'm sorry, Dr. Dieky.
Yeah.
5 minutes left.
Okay.
Yeah.
Let me. Sorry, I pushed the. Okay. So this is the one that I discussed earlier is the model is already in closed loop, or the model is autonomous. So it is not related to controller synthesis or controller design. Recently, verification can also be used for designing a controller, as I mentioned in the beginning of this presentation. So what is the scheme in this case? So it is quite similar with before. So we have a model, and then we have a specification, and then we want. So in this case, the model is autonomous. Non-autonomous. So it has some control variables or input variables. And so in this case, our purpose is we want to design a controller such that the behavior of the closed loop system satisfy the specification. Again, there are 2 possibilities. We may be able to design a controller, and in this case, we can guarantee that the behavior of the controller will always satisfy the specification. Or we may not be able to design such a controller. The verification problem and the controller synthesis problem is different. And in this case, the verification problem is easier compared to synthesis problem, because in verification problem, the model is already fixed. So we just have to verify the behavior. But in synthesis problem, you need to design a controller such that the behavior of the closed loop system satisfies the specification. And this is a more difficult problem because we need to synthesize something. We need to come up with something. So this is an example of a tool or a method to controller synthesis for nonlinear systems. The name of the tool is SCOTS. So this is a tool for the synthesis of symbolic controller. It uses the name symbolic controller in order to differentiate with the traditional controller. So symbolic controller usually means the controller that is synthesized by using formal verification. Sometimes many authors use the name symbolic controller. So here we have a kinematic model, as you already know. The kinematic model is a nonlinear ordinary differential equation because it has sines and cosines in the right-hand sides. So this is an example of the results. So as you can see here, we have a particle, and then the initial position is here. This is the initial position, the green area, and then the red area is the destination. We want to reach that, but in this area there are also some obstacles. The obstacles are the blue area. So in this case, the specification in English is like this. So we want to reach the red area if we start in the green area, but when we reach the red area, we have to avoid the blue area. So this is called the reach avoid specification. We want to reach some states, but while reaching the states, we want to avoid some bad states or dangerous states, something like that. Okay. Yeah, formal verification has also been used in combination with artificial intelligence. So this is an example of the paper by some authors in computer aided verification conference. So this conference is a competitive one because it is very difficult to be accepted there. So it is a very good one. And in this paper, they apply the formal verification to deep neural networks. If you are working in artificial intelligence or deep learning or big data, I think it is not new to you. So deep neural networks have achieved impressive experimental results for image classification, or also in other fields, I think. However, if there is a perturbation or changes in the image, the results of the classification may change. For example, when the lighting condition, so at night and also at noon, the same objects may be classified differently, something like that, or changes in the camera angle. It may also change the classification results by using deep neural networks. So in this paper, they want to verify the safety. They want to verify the safety of image classification decision. So they want to verify how much perturbation. They want to verify if we define some level of perturbation, they will check whether the deep neural network is can handle this perturbation or not. So if the outcome is yes, then we can guarantee that if the perturbation is still beyond the beyond that level, then the result will not be changed. But however, if the perturbation is above that, then it may be changed, something like that. So this is one example of the application of formal verification in combination to artificial intelligence. I think this is the last slide of my presentation, and these are the references that I use. The first one is the summer school that I attended during my PhD, and it gives some good introductory background to formal verification. And then the second reference is a book on model checking, which is a good book, I think. And then the third one is the reference for formal verification for nonlinear systems, as you seen in the slide, in the reach avoid specification. And the last one is the combination of formal verification and also artificial intelligence. Okay, I think this is the presentations from me. Thank you for the time, and okay, thank you. Welcome.
Yeah, thank you so much, Dr. Dieky, for new topic, especially for me, because I just know about formal verification. Okay, for the last session, for the last speaker, the most beautiful speaker. Yeah, for Dr. Hani. Hello, Bu Hani.
Hello, Mr. Akam. Yes.
Yeah. The last speaker, the last presentation for Dr. Hani. Time is yours.
Yes, thank you, Mr. Akam, for this time. For this time, I will use Indonesian for my presentation. So I would like to say sorry for Professor Kim. Okay, I will share my presentation. Sudah bisa melihat presentasi saya? Sudah?
Ya.
Oke. Terima kasih atas kesempatannya pada hari ini untuk bisa mengisi workshop series bersama para pakar dengan Profesor Kim, Pak Subchan, dan Pak Dieky. Pada presentasi yang terakhir ini saya mau memberikan, sepertinya bukan memberikan, sharing saja sedikit mengenai data driven model and its application in USV. Dengan saya Tahiyatul Asfihani. Saya, Pak Dieky, dan Pak Subchan berada pada istilahnya pada organisasi yang sama atau menjadi dosen yang sama di Departemen Matematika di Institut Teknologi 10 November. Bicara mengenai data driven model, maka kita harus mengenal yang namanya model. Tadi pada sesi sebelumnya sudah sempat disinggung oleh Pak Subchan dan pembicara sebelumnya oleh Mr. Kim juga, bahwa model itu merupakan sebuah bentuk sederhana dari sebuah sistem yang bisa direpresentasikan dalam suatu physical model atau miniatur, atau bisa dikatakan atau prototype. Nah, ada juga bentuk sederhana dari suatu model yang berupa simbolik seperti halnya Matematika Model. Apa sih kelebihan ataukah kenapa sih harus ada model terlebih dahulu? Nah, ada beberapa desain praktisi seperti halnya model based control. Nah, di sini model matematika sangat diperlukan sehingga bisa menghemat biaya atau cost bagi praktisi untuk bisa membuat istilahnya adalah bagian kecil atau miniatur dari sebuah sistem atau full scale system atau sistem secara keseluruhan. Tadi sudah sempat disinggung oleh dengan Pak Subhan bahwa apa yang kita definisikan pada model tentunya tidak bisa merepresentasikan seluruhnya oleh sistem secara kenyataan. Oleh karena itu di sini merupakan model adalah bentuk sederhana. Misalkan saja pada desain kapal, orang ahli perkapalan akan mendesain miniatur atau prototipe kapal sebelum mereka mendesain full scale-nya. Sebelum mendesain full scale untuk melihat atau menganalisa bagaimana behavior kapal tersebut sehingga tidak membuang atau membuang biaya yang cukup besar. Nah, model di sini saya memfokuskan bagaimana kita membentuk sebuah mathematical model berdasarkan pada data yang berasal dari physical atau prototype. Nah, di sini data driven model, from data to model. Bagaimana kalau kita misalkan punya beberapa data. Data yang ada misalkan mengenai position atau posisi, kemudian sudut roll atau roll angle, terus kemudian dengan yaw angle. Kita mempunyai data tersebut berdasarkan pada sensor, kemudian kita tidak tahu, oh ini nanti behavior sebenarnya pada kapal itu sendiri seperti apa. Oleh karena itu dibutuhkanlah sebuah model untuk bisa merepresentasikan, oh ini nanti keterhubungan antara posisi dengan role, kemudian yaw itu adalah seperti apa. Sehingga di sini nantinya mathematical model bisa merepresentasikan tersebut. Nantinya ketika kita bicara mathematical model itu adalah bagaimana kita melihat output, kemudian kita tarik garis ke belakang, bagaimana suatu sistem itu terbentuk dengan adanya input yang ada. Jadi kita nanti mathematical model di sini adalah bagaimana membentuk sistem atau di sini x dot sama dengan fxu. Nah, kemudian data yang kita dapat itu adalah yang di output dengan input yang sudah istilahnya adalah yang diketahui atau input yang diberikan. Kemudian bicara data driven model, berarti kita nantinya untuk ini adalah mengenai sistem identifikasi. Sorry, I have bicara sistem identifikasi ini nanti kita akan melihat bahwa sebentar, PowerPoint saya ini sepertinya bagaimana kita mendesain atau membuat sebuah mathematical model dari berdasarkan pada data. Nah, di sini nantinya kita akan ada data, tetapi data yang tersedia itu adalah data yang tidak merepresentasikan semua. Misalkan saja pada yang kita teliti adalah mengenai kapal tanpa awak. Jadi yang bisa kita lihat di sini berdasarkan pada sensor adalah mengenai sudut roll, sudut yaw, dan posisi. Padahal secara gerak atau secara manuver, kapal itu mempunyai gerak lain selain itu. Nah, bagaimana kita bisa mensiasati supaya informasi data tersebut bisa lengkap? Nah, di sini kami menggunakan data assimilation. Data assimilation itu merupakan optimal estimasi atau metode estimasi yang optimum. Di sini data asimilasi atau asimilasi data menggunakan matematika model atau model matematika berdasarkan atau dikoreksi dengan data pengukuran. Nah, di sini kenapa balik lagi? Padahal kita tujuannya adalah mencari model matematika, tetapi pada saat menggunakan data asimilasi, kita harus menggunakan model matematika. Pada sistem identifikasi tidak harus melulu adalah mendefinisikan bagaimana kita membuat model matematika itu bisa saja kita mendefinisikan terlebih dahulu dengan merujuk pada penelitian-penelitian sebelumnya. Kemudian bagaimana suatu model matematika yang berdasarkan pada data tersebut bisa diperoleh, yaitu dengan representasi dari parameter. Nah, data asimilasi ini salah satu contohnya seperti yang sudah dilakukan, salah satu contohnya adalah Kalman filter. Kalman filter ini digunakan untuk sistem yang linear, kemudian ada extended Kalman filter digunakan untuk sistem yang non-linear, kemudian ensemble Kalman filter dan unscented Kalman filter juga digunakan untuk sistem yang non-linear. Akan tetapi di situ ada perbedaan antara extended Kalman filter dan ensemble Kalman filter dan unscented Kalman filter, yaitu pada saat extended Kalman filter digunakan suatu sistem nonlinear dengan cara pelinearan seperti yang dilakukan oleh Prof. Kim. Kemudian untuk ensemble Kalman filter tidak perlu dilakukan nonlinear, tetapi di situ pendekatannya adalah pendekatan dengan membangkitkan beberapa ensemble data pada saat input awal. Kemudian untuk unscented Kalman filter adalah metode asimilasi data dengan pelinearnya dengan menggunakan pendekatan statistik, yaitu menggunakan transformasi unscented. Nah, setelah semua data itu lengkap, istilahnya adalah kita bisa mengetahui beberapa data yang kita perlukan supaya bisa mengetahui parameter sehingga bisa melengkapi model matematika tersebut. Nah, setelah mendapatkan itu kita bisa mendefinisikan parameter berdasarkan pada regresi atau dengan menggunakan recursive least square. Oke. Nah, ini nantinya kita akan aplikasikan atau cara mendapatkan sistem identifikasi pada kapal tanpa awak atau unmanned surface vehicle. Ini adalah kapal tanpa awak kami dengan dimensi kapalnya adalah sebagai berikut. Nah, dengan data atau sensor yang kami peroleh adalah posisi, kemudian ada sudut yaw dan sudut roll. Nah, sistem identifikasi pada kapal tanpa awak, kita istilahnya harus mengenal terlebih dahulu apa saja sih yang harus kita istilahnya mau variabel-variabel mana atau sistem ini harus terbentuk seperti apa. Pada data yang tersedia, di situ tadi sudah disebutkan adalah mengenai posisi, roll, dan yaw. Padahal di gerak sendiri, gerak kapal itu terdiri atas gerak translasi itu 3, gerak rotasi ada 3. Nah, di sini ada gerak translasi yaitu surge, sway, dan heave. Kemudian untuk gerak rotasi itu sendiri ada roll, yaw, dan pitch. Nah, pada penelitian ini yang kami amati itu adalah mengenai gerak kapal tanpa awak, mengenai gerak manuver. Sehingga yang kami amati adalah maksimal di sini adalah 4 derajat kebebasan, yaitu surge, sway, yaw, dan roll. Untuk variabel-variabel yang lain kita tidak memperhitungkan hal tersebut karena kita semakin kompleks suatu sistem kita sesuaikan dengan kebutuhan. Seperti itu. Terus kemudian berarti kita nanti data yang kita punya adalah roll, kemudian yaw, dan tadi adalah posisi. Nah, ini adalah data pengukuran yang ada. Nah, di sini berdasarkan pada sudut yaw dan sudut roll, di situ bisa kita dapatkan kecepatan sudut yaw dan kecepatan sudut roll dengan cara mengolah data yang ada di sudut yaw dan sudut roll. Seperti itu. Kemudian untuk model matematika, kenapa di sini disebutkan semua atau di sini adalah apa saja sih yang harus kita definisikan di mathematical model yang kita perlukan untuk keperluan kami di gerak manuver kapal tanpa awak, yaitu surge velocity, kecepatan surge, kecepatan sway, kemudian kecepatan sudut yaw, kecepatan sudut roll, posisi sudut yaw, sudut roll. Nah, di sini pada yang terakhir di situ ada dynamics of x, y, k, n. Nah, apa sih x, y, k, n tersebut? Kalau berdasarkan pada model matematika kapal tanpa awak, bahwa itu adalah merupakan sebuah fungsi dari variabel yang masih mengandung beberapa variabel. Dan nantinya nilai x, y, k, n itu harusnya bisa kita prediksikan supaya kita bisa mengetahui bagaimana hubungan antara kapal, istilahnya ketika kapal berlayar di laut atau di air akan menimbulkan sebuah koefisien hidrodinamika. Nah, XYKN itulah yang merepresentasikan hal tersebut. Kemudian dari berdasarkan pada matematika model tersebut, maka dengan observasi data atau data pengukuran kita menggunakan unstandard Kalman filter untuk mendapatkan nilai-nilai atau estimasi dari kesemua variabel yang ada di matematika model. Nah, di sini model dinamik, di sini ada U, P, R, V, di stat variabelnya ada kecepatan sway, kecepatan yaw, kemudian kecepatan roll dan kecepatan sway. Nah, di sini model dinamika modelnya, kemudian seperti yang saya ceritakan tadi bahwa di sini ada X. X di sini merupakan suatu fungsi dari variabel U, V, R, V, dan seterusnya. Nah, begitu juga pada X, Y, K, N, dan seterusnya. Nah, ini nantinya nilai yang ada di sini nantinya X itu sendiri, X besar, itu harusnya kita bisa definisikan sebagai variabel baru supaya nanti bisa kita dapatkan nilai X besar. Karena nilai X besar itu sendiri untuk tidak diketahui. Karena dia bergantung pada VR dan seterusnya. Kenapa tidak diketahui? Karena nilai XUU, XVR, dan XVV, XRR, X delta ini tidak kita ketahui. Nah, tujuan dari sistem identifikasi nantinya adalah menentukan XUU, XVR, dan seterusnya. Dan itulah yang disebut dengan koefisien hidrodinamika. Nah, di sini kita definisikan mathematical model of augmented system. Karena tadi yang kita ketahui adalah kinematika model, ada posisi, kemudian sudut roll dan sudut yaw. Dan ini adalah dinamika model. Nah, untuk X besar, Y, K, N, untuk penelitian ini kita definisikan sebagai third order Gaussian model. Jadi pendekatannya adalah turunan ketiga dari X itu adalah berupa Gaussian model. Atau di sini disimbolkan X triple dot sama dengan white noise. Seperti itu. Nah, berdasarkan pada augmented system ini, nantinya akan kita estimasi dengan menggunakan unstandard Kalman filter. Pada penelitian ini, XYKN dijadikan sebagai variabel, oleh karena itu maka mathematical model ini adalah merepresentasikan adanya augmented system. Karena sebenarnya X besar itu sendiri adalah sebuah fungsi antara beberapa variabel dengan parameter yang tidak diketahui sebelumnya. Kenapa parameter atau koefisien hidrodinamika itu tidak diketahui? Karena sebenarnya secara real bahwa parameter hidrodinamika atau koefisien hidrodinamika bersifat time varying atau bergantung pada waktu. Akan tetapi pada penelitian ini kita tidak meneliti nilai dari koefisien hidrodinamika secara time varying atau bergantung pada waktu. Seperti itu. Nah, estimasi dari augmented system dengan menggunakan unstandard Kalman filter. Setelah kita estimasi bahwa hasil dari estimasi dengan menggunakan unstandard Kalman filter menunjukkan bahwa data yang estimasi bisa mencakup atau error dari estimasi terhadap data pengukuran adalah kecil seperti itu. Di sini ada gambar dari sudut yaw, kemudian sudut roll dan posisi dari kapal tersebut. Ini adalah data posisi kapal yang berbentuk lingkaran karena ada beberapa uji coba ataukah data yang kita pakai, yaitu data yang kita pakai adalah turning circle dan berbentuk zigzag. Makanya di sini bentuk dari posisi kapal atau posisi yang sudah dilalui kapal adalah berbentuk lingkaran seperti itu. Nah, untuk identifikasi koefisien hidrodinamika seperti yang sudah saya ceritakan tadi, bahwa identifikasi koefisien hidrodinamika sebenarnya adalah berhubungan dengan sistem identifikasi. Nah, koefisien hidrodinamika itu sendiri adalah parameter dari sistem model parameter dari model dinamika kapal. Nah, bagaimana kita bisa menentukan koefisien hidrodinamika yang ada? Tadi sudah disebutkan bahwa koefisien hidrodinamika berada pada fungsi X besar, di mana X besar itu adalah gaya pada surge, gaya dan momen pada surge. Nah, di sini di sini ada XUU, ada XPR, ada XPV. Itu artinya adalah bahwa gaya X yang dipengaruhi oleh U dan istilahnya adalah X yang dipengaruhi oleh kuadrat dari U atau turunan kedua dari U. Terus kemudian ada XVR, ada XVV dan XRR dan X delta. Di sini delta itu adalah sudut radar, inputan dari sistem kapal tanpa awak ini. Jadi kalau kita melihat kapal, istilahnya bukan baling-baling, yang paling belakang sendiri, flap yang berada di belakang yang sebelahnya dengan baling-baling itu adalah radar atau di sini disimbolkan dengan delta. Nah, bagaimana kita bisa menentukan koefisien hidrodinamika di kapal tanpa awak tersebut? Nah, kenapa sih kok kita menentukan koefisien hidrodinamika? Karena kapal yang bentuknya berbeda akan mempunyai koefisien hidrodinamika yang berbeda pula. Oleh karena itu, koefisien hidrodinamika ini mendefinisikan atau bersifat unik sesuai dengan bentuk dari kapal itu sendiri. Seperti halnya representasi dari parameter suatu model. Nah, di sini tadi sudah kita melakukan estimasi dengan Kalman filter. Nah, kita sudah dapat data dari Kalman filter yaitu X, U, dan V. Karena data-data tersebut tidak kita miliki, sehingga kita harus mengestimasinya dengan Kalman filter. Jadi tujuan asimilasi data di sana adalah untuk melengkapi persamaan ini, supaya persamaan ini bisa diselesaikan atau kita bisa mendapatkan koefisien hidrodinamika. Oke, terus kemudian di sini R, V, dan R itu adalah sudut yaw dan sudut roll. Itu kita peroleh dari data yang kita dapatkan dari sensor. Terus kemudian delta di sini adalah sebagai input. Nah, ini adalah sistem identifikasi dari sistem parameter. Setelah kita mendapatkan data dari estimasi menggunakan unstandard Kalman filter, kemudian ada data dari pengukuran yang sudah kita peroleh dari sensor, kemudian kita mengetahui input yang ada, sehingga kita bisa melihat persamaan ini sebagai persamaan regresi atau istilahnya adalah persamaan linier. Kenapa dikatakan sebagai persamaan linier? Karena nilai U nantinya akan diinputkan sebuah nilai. Nanti ini ketika persamaan ini nantinya akan dibentuk menjadi persamaan linear dan akan dicari nilai XUU, XVR, XVV, XRR, dan X delta. Singkatnya ataukah mudahnya ini bisa kita peroleh dengan menggunakan regresi. Dan juga bisa dicari dengan menggunakan bisa dengan recursive least square atau dengan yang lainnya. Nah, itulah yang bisa kita dapatkan setelah dapat hidrodinamik koefisien, maka kita pasti akan mengetahui karakteristik dari kapal tersebut. Kenapa ini sangat penting buat terutama untuk kapal tanpa awak atau kapal yang istilahnya untuk sebuah misi, karena ketika kita sudah bisa mengetahui nilai dari koefisien hidrodinamika, maka kita tahu bahwa kita nanti bisa memodelkan dengan mudah. Atau dengan kata lain, kita bisa memprediksi behavior dari sebuah kapal tersebut. Nah, ini hasil dari koefisien hidrodinamika yang ada, yang berdasarkan pada penelitian kami.
Mohon maaf, Bu Hani.
Ya.
Waktunya 5 menit lagi.
Oh, terima kasih Pak Ageng. Nah, ini adalah koefisien dinamika dari kapal tanpa awak kami. Nah, ini ketika sudah bisa mendefinisikan ini, maka kita dapat dengan mudah kita bisa membuat model matematika sehingga nanti apabila kita nantinya mempunyai lawan, maka kita bisa diprediksi oleh lawan nanti gerak kapal ini akan kemana seperti itu. Apalagi ini kondisinya adalah kapal tanpa awak, begitu. Kalau misalkan misinya diketahui seperti itu. Saya rasa cukup presentasi sharing saya. Saya kembalikan ke Pak Hakam.
Yeah, thank you very much, Dr. Hani. And the next session is discussion. There are many questions directly chat to me, but I will choose several questions from audience. The first question comes from Mr. Heri Purnawan, one of doctoral student in Matematika ITS. The question for Professor Kim, I will read the question. The first question is relating to FMINCOM MATLAB Toolbox, Professor Kim. I'm doing a simulation about an NPC for autonomous vehicle with obstacle avoidance, but I have some problem. Sometimes I found solver stop prematurely. How can I fix it? How to analyze the problem? In that case, I use an anonymous function at U for the nonlinear inequality constraint for the states. Yeah, maybe Professor Kim can give.
Hello?
Yeah, Professor Kim.
Can you hear me? Yeah.
Yes.
The question is about the non-convergence problem, especially for collision avoidance. Is it right or?
Yeah, about FMINCOM. And there is a statement solver stop prematurely. How can it fix? The question I written in chat box.
In the FMINCOM toolbox, right?
Yeah.
Yeah. I'm not sure. I'm understanding perfectly about the problem, but the collision avoidance is the inequality constraints. So actually, that makes the cost is not non-convex problems. So it has many local minima, and then we can find many local minimas near the initial condition of the optimization parameters. So depending on the initial conditions, it can be falling into the local minima problem, even if somebody used the FMINCOM, the function, MATLAB function. So I think there is no perfect remedy for that problem, but the initial condition and then the O-prime optimization can be helpful for setting up the initial conditions and then slightly modifying how to use FMINCOM with the proper cost function. And then as I show you the Kuhn-Tucker variable L in my slide, for considering the inequality constraint into the augmented cost performance index, that will be very important. There is a Kuhn-Tucker variable. So, but I'm not sure about how to use in the FMINCOM that kind of things because I didn't use FMINCOM for my problem. So I created the line by line for my source code in the MATLAB for optimization as I derived in my slide. So this could be helpful or not.
Okay. It means still try and error, yeah, Prof. Kim, to identify what happen.
It's
Okay.
depending on the case by case and the problem definition.
Okay, yeah. For the next question, it comes from Mr. Abrari Nur Hasmi. Hello, Mr. Abrari.
No.
Can you turn on? Yeah. May you directly say to Professor Kim directly your question? Yeah.
Yes, Professor Kim, I would like to ask about the feasibility to compute the NMPC at the embedded system. I mean, we know that the embedded system has slower computational speed and also has smaller memory and so on and so on. So I'm afraid that if we implement that in a embedded system, it will be impractical. Thank you for the opportunity.
Yes, I can see your question from the chatting window, right? See, I think the nonlinear model, actually linear MPC can be easily applied to the real system with the embedded system because it is straightforward to predict the future state. But NMPC can be applied, I think so. NMPC can be applied fast enough to the embedded system with adjusting the large n, the size of the receding horizon prediction step. If you decrease the prediction step, that can be applied. For example, just 2 samplings and 3 samplings prediction can be really helpful. So, but 10 seconds, 100 points prediction will not be feasible up to now. So depending on the system, the embedded system can do that kind of things, especially for higher level, not the attitude control, not actuator control. For the trajectory planning or just making some outer guidance comment to the inner loop. So embedded system can be applied, I think so. And then nowadays, the embedded system used for the off-board for PIXOC. I think you guys a PIXOC system for UAVs and drones and USV. So the PIXOC nowadays, the Open Loop Society is testing MPC for the PIXOC, the autopilot system. So I think in the near future, nonlinear model predictive control can be applied in the open source autopilot community as well.
Okay. There is again from Mr. Abrari for Dr. Hani. Apa yang harus dilakukan apabila data yang diperoleh tidak memiliki selang waktu yang seragam dan frekuensi sampling terlalu besar atau terlalu sedikit? Dr. Hani, respons.
Ya, untuk data yang diberikan di situ selang waktu yang seragam. Nah, untuk frekuensi yang terlalu atau data terlalu sedikit, jadi kalau kelebihan dari data asimilasi atau assimilation data itu adalah bisa menggunakan data yang jumlahnya sedikit. Karena di dalam asimilasi data menggunakan mathematical modeling juga sebagai prediksi. Data hanya digunakan sebagai frekuensi. Dan bagaimana apabila data yang mempunyai selang waktu yang tidak memiliki waktu yang seragam. Nah, untuk data yang tidak memiliki selang waktu yang seragam bisa karena itu data karena asimilasi data berdasarkan pada mathematical modeling dan itu berdasarkan istilahnya adalah per waktu seperti itu. Sehingga nanti untuk datanya bisa di fitting. Kalau bisa digunakan fitting karena ada beberapa penelitian yang bisa mencari selang-selang yang kosong seperti itu untuk datanya. Tetapi kalau misalkan dari data seperti halnya sekarang, untuk data sensor, saya rasa untuk sensor yang memiliki akurasi yang cukup baik akan bisa memberikan data yang cukup seragam untuk selang waktunya. Mungkin itu jawaban saya, Pak. Respon saya, Pak Hakam.
Yeah, thank you so much to Burhani. And there is the last question from Mr. Marsudi for Dr. Subhan. How do we design a cost function in an optimal control problem for the dynamic system to ensure stability? Maybe Mr. Swan can give you a response.
Okay, thank you very much, Pak Marsudi. How are you, Pak Marsudi? Okay, regarding the cost function or design a cost function in optimal control problem, it's really depend what actually we want to optimize. Yeah, but you have to remember, if we give some linear control objective function, usually when you derive, when you create Hamiltonian, when you develop Hamiltonian, and if it is as well the dynamic system is linear and control, then it will give some problem. But if you give some, the cost function, let's say, as what we discussed in this class, in this workshop, like Prof. Kim mentioned, maybe quadratic, and if it is fortune, the dynamic system as well is nonlinear in control, then it will be easier. So I think the simple answer is like this. But if you use a linear objective function or cost function in control, and also the dynamic, if it is unfortunate that the dynamic as well is linear in control, then the Hamiltonian later, when you derive the first stationarity condition, the control will be disappear. Then what happens is usually the computational result, the controller performance will be bang or singular. That hopefully can answer little bit of your question. Thank you.
Yeah, thank you, Mr. Suhan. And finally, we are in the end of the session, but I'm sorry if there is a question, there are questions not answered yet, but this is not the end of the workshop, Mr. Subhan.
Yes. I will close the session later.
There is the next workshop about mathematics applied and computing science, but the end of the session for Mr. Suhan will be give the speech maybe for the next workshop for Mr. Suhan, please.
Okay, thank you very much for the time. Sorry, Prof. Kim, I will speak a little bit in Indonesia and in English. So I would like to say thank you very much for all the speakers, especially Prof. Kim from far away from South Korea. Hopefully next year we will meet in Indonesia or in Korea again, Prof. Kim, yeah, rather than in virtual like this. Yeah, thank you, Pak Dieky, Burhani, and all participants. As I mentioned to you at the opening speech, we will have a 4 series of the workshop. The next series, Prof. Kim will talk about cooperative mission with heterogeneous UAV. Still about UAV, but cooperative mission here. And the second speaker would be Professor Erna from the Department of Mathematics. She will discuss about Kalman filter application for navigation, guidance, and control. There will be another 2 speakers. I will still looking discussion with the speakers at this time. Hopefully, we will post our poster soon on the media or on the web of Department Mathematics. Hope to see you again on the 24th of September. Please put it on your agenda that we have the same meeting, the same workshop at the same time with Prof. Kim, Prof. Erna, and another 2 speakers. Thank you very much, Pastor Hakam, for become moderator at this meeting. Thank you very much. Many thanks, Prof. Kim, ya. Have a nice lunch,
Thank
Prof.
you.
Kim.
Thank you very much.
Okay. Thank you, Pak Hakam. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Subchan. And I want to say thank you again for all speakers, especially for Mr. Kim, Professor Kim, and Mr. Subchan, Dr. Dieky, and Dr. Hani. And thank you for all audience who has participated in this workshop. And I hope we can meet again for the next workshop series. And the last say, wassalamualaikum warahmatullahi wabarakatuh. See you later. Terima kasih, Bapak Ibu.
Oke, thank you Bapak Ibu semua ya. Semoga bermanfaat. Prof. Kim, thanks a lot Prof. Kim. Hilang sudah Prof. Kim. Sudah pergi ya Prof. Kim ya.